We're going to go through lots of examples of the different types of equations here. This will be a skill we work on all year long, so you don't have to perfect it right now, but you need to start understanding, applying, and asking questions as you face challenges. So for a molecular equation, it's all about writing the right chemical formulas, counting your atoms to balance it, and then showing your states of matter as well. We have aqueous hydrochloric acid, and we would remember that hydro is when it's bonded with no O, so HCl, sodium bicarbonate, and we will not be given any polyatomic ions on our periodic table. There's far less name and formula writing on this AP test, but we do want to kind of refresh ourselves, and as we're practicing, definitely use the periodic table from Chem 1, and we've got lots of extras for you. Hopefully we know the formulas for water, CO2, and NaCl. And sometimes when things break apart and come together in different ways, it's a little bit challenging to balance. So you just need to take your time and double check. We've got some complete and some net ionic equations down here for equations that already have our symbols: aqueous, solid, and liquid. So when it is aqueous, we would need to think about, does it get broken apart or stay together based upon those rules? Alkali metals, nitrates, and ammonium is broken apart. Strong acids are broken apart. Strong bases are broken apart. And all other aqueous things would often be together. And we even have an example or kind of a weird exception here, so we'll talk about that. But K2SO4 is aqueous. Here we have an ionic compound that it tells us is aqueous. It's not an acid, it's not a base, it's not covalent, it is a metal and nonmetals. So since it defines it as aqueous, that means that it is able to separate. Acetate is one that you used to have to memorize as always soluble and has kind of been removed from that list. But if we have ionic and it tells us it's aqueous, that means that it is separated. Potassium acetate is right there. And then lead sulfate, it defines to us as a solid. Solids stay together, liquids stay together, and gases stay together. Aqueous gets split apart if it's ionic and it tells us it's aqueous, if it's a strong acid, or if it's a strong base. So here I have separated everything. And note that rather than keeping this as K2, I recognize that that means there's 2 potassium ions floating around. But right here with the sulfate, it doesn't dissolve and dissociate into sulfur and 4 oxygens. It stays as the polyatomic ion sulfate. So I have my potassium sulfate, lead acetate, potassium acetate, and then it told me I had a solid lead sulfate. When we're looking at this, we can even jump ahead maybe to the net ionic by thinking about, well, what are the things that go from aqueous to solid? The lead, the sulfate becoming lead sulfate. Notice down here, I don't have my states of matter. AP and the College Board has kind of decided that as we write things separate and together, it's kind of implied what states they are in. So we don't necessarily need to write that in order to get the full points there, which is nice. Here we have nitric acid and calcium hydroxide. If we flip back to the other page, we see that those are both considered strong. So we write them as separate. We write it as separate. Calcium nitrate, it told us it was aqueous. But we also know that nitrate will always be aqueous. And then right there, water is a liquid, so it stays together. So the calcium and the nitrate don't change from left to right, but the hydrogen and the hydroxide combine to make water. Even though it's 2, 2, and 2, we often reduce that to the lowest coefficients when we simplify our reactions. Right here, it gives us a molecular equation of sodium bicarbonate breaking down into products. But it is a solid, which doesn't get ionized, a solid, which doesn't get ionized, a liquid, which doesn't get ionized, and a gas that doesn't get ionized. So every version of this equation is the exact same. We don't break something apart just because it's ionic if it's written as a solid, liquid, or gas. On C, it asks for just the net ionic equations. You will, with practice, be able to go straight from a word equation down to here, but it's important to kind of think through that process while we're practicing. It tells us that aqueous solutions of calcium nitrate, so I write CaNO3 aqueous, and ammonium sulfate, NH4, ammonium 2, SO4 aqueous, react, forming a precipitate. It didn't tell us what our products were, nor what the precipitate was. We will talk about the different types of reactions, but the most common that we will see is a double replacement, where we swap partners, and the outsides, the calciums and the sulfates go together, and the insides, the ammoniums and the nitrates go together. So that makes ammonium nitrate aqueous and calcium sulfate solid. And the way we can know what is aqueous and solid is the solubility rules. Ammonium is always soluble, nitrate is always soluble, and calcium sulfate is not on that list. So it has to be the precipitate by process of elimination. Our original reactants were all solutions, so those are separated. And then we write the things that are together and aren't together. That allowed us to cross out our ammonium and our nitrate, or to know that the calcium and the sulfate would be our product. With practice, we could think about, well, I know that nitrate won't be in my precipitate. I know that ammonium won't be in my precipitate. So the precipitate has to be the reaction of calcium and sulfate to make calcium sulfate. Here we have hydrofluoric acid solution reacting with sodium hydroxide solution. It's another double replacement. HF, NaOH makes NaF and H2O. We wrote the states in there. The solutions mean AQ. Right here, as I looked at NaF, I knew that sodium never forms a precipitate. So it is ionic and therefore aqueous. And H with OH to make H2O is pure water. But probably, maybe at first look, the most confusing thing here is I wrote an aqueous thing still together. HF is aqueous, but it is an acid because it starts with an H. But it is not HCl, HBr, HI, HNO3, H2SO4, or HClO4. It is not one of the 6 strong. Therefore, it is weak, and 90% or more of the molecules are bonded together, and we need to represent them that way. Sodium hydroxide is strong, and we write it separate. Over here, we still use our solubility rules, and then we still have water. So our reaction might look different than we expected. But when we see acid, we have to really think, is it going to be separate or together? And then we need to know our strong and our weaks for acids and bases. And we have our reaction right here. So up above, we had a reaction of a strong acid and strong base and a weak acid and strong base. There are similarities, but we see that there's also some important differences in terms of how we show it. On part D, the last part for now, and we'll do more reactions throughout, we're writing the molecular, the net ionic, and if we need it, the complete ionic as we go through. So calcium metal, that means Ca is a solid, reacts with oxygen as a gas. It tells us that. Well, the only things that 2 separate atoms can do is to come together and to make a compound. They're going to bond together based upon their charges, and they're going to make calcium oxide. This is an example of a synthesis reaction. This is another case where, while we're practicing, we'll use our Chem 1 periodic table a lot to think about these. You very rarely will have to predict products off the top of your head, but we need to be familiar with those things. We need to be able to come back to the skills that we built before and try to use those again. This is a solid, as it said, this is a gas, and then this is a metallic compound. There's no water, so it's just a solid. It's not metallic, it's ionic. Here we have magnesium ribbon. Magnesium is a solid placed in a solution, so that's aqueous copper chloride. This is an example of a single replacement. The element by itself comes in, the element within the compound that's most similar, metal and metal, or cation and cation, it replaces it. The magnesium's in and the copper is out. The magnesium chloride is aqueous because we were in solution before, and the copper is a solid. And if we write that down here, the way it would really look would be the magnesium was a solid piece with no charge. When we put it in, the copper and the chloride were ions floating around. The magnesium becomes an ion floating around as it dissolved, and the chloride remains dissolved, and the copper starts to form as a solid. Magnesium reacts with the copper ions to make magnesium ions and copper. Really simplifies this down that the chloride is just a part of the solution that's happening. So we've got our molecular, our complete, and our net ionics. Magnesium hydroxide powder, we need to be able to write that formula, MgOH2. It's a powder, so it's solid, is dehydrated. Take water out. So we would take H2O out, leaving us with MgO. This is another place, look on your periodic table as we practice, and we would see why it follows that pattern. Far less memorization for AP Chem, but we want to refresh ourselves again. Ethanol, which it gave us our formula, burns in air, and hopefully we know the element or the gas responsible for things burning in air is oxygen. So it's reacting with O2 in all combustions. And this is something you need to know. It makes CO2 and H2O. So then there's a lot of back and forth and balancing that can go on here. We wouldn't necessarily know the state here, and sometimes it makes water, sometimes it makes water vapor, but all of these are pure substances. We wouldn't have anything dissolved or any ionic rules. So we would look at that, and then it would just come down to the back and forth balancing. And lastly, we have a solution of sulfuric acid being neutralized by a solution of barium hydroxide. Sulfuric acid, H2SO4, we're going to recognize that by repetition that it's strong. Barium hydroxide, it's got OH, barium's in column 2, so it's a base, and it's a strong one. Acids and bases always neutralize to make water, and I didn't correctly balance it here, so I'll fix this as we go. There we go. But it says, it doesn't say this, but barium goes with sulfate. We should maybe have a little bit more of a tip here that a precipitate forms. So I'm going to add that, forming a precipitate. And I'll add that on the other instructions as well. But what happens, or what we see happen here, is that our completely ionized acid, our completely ionized base, when they swap partners, they make water, but they also form something that's insoluble, or a precipitate. So our complete and our net ionic look very similar here. And as we look at them, not only have I balanced out the hydrogens, sulfurs, oxygens, and bariums, I also recognize that I've got 2 positives with 2 negatives, 2 positives, 2 negatives, and my charges are completely neutral here. Back up in this example, I've got a +2 charge and a +2 charge. So I am balancing both my atoms and my charges as I write net ionics, complete ionics, or molecular